My talk is about some work we've been doing now for a number of years. The research is happening, this work is happening in the context of a series of EU research projects. So there was SET IoT, which was one big project, and then followed by GHOST, another one. The next one was Configo, with medical applications, medical network applications. Then there was IoTac with IoT applications, and currently it's DOS, which also is related to the IoT. And I have won another grant. Of course, winning grants means that you write a lot of stuff. So not just getting, doing the research, but writing a lot of proposals. And the new one is going to be starting in January. So that's part of my activity is, writing, coming up with ideas and writing proposals. And then from that on, doing the research and then supervising PhD students and so on and so forth. So that's the work. So the work we've been doing is a matter of, on the one hand, detecting attacks, but on the other hand, also figuring out now how to mitigate them. Okay, because when you have an attack, you need to mitigate them, and you should also, of course, if you want to mitigate them, do them at some minimum cost, because attack mitigation, getting out of an attack and then mitigating it, is a heavily processing-oriented activity. So that's one of the research questions we're looking at: how to mitigate them and how to mitigate them at minimum cost. So these are some of our publications. We tend to publish mostly in journals. Why? Because of the Polish Academy of Sciences, which has an interesting numbering system. So this journal, for instance, Internet of Things journal, has maximum points, 200 points. Forensics and security has maximum points, etc. So we try to, IEEE network has maximum points. So we try to submit to journals which have a high pointage system. I've just had one accepted in the journal Information Fusion. It's not on the list. So we go, or Proceedings of the IEEE, it's not on the list. So we go for journals which have a high point system and not for conferences where, sometimes there's a debate, is this that type of conference or that? Of course, there are extremely good conferences, but unfortunately, we are working within a system, which is why there are so many journal papers, okay? The systems we're looking at are systems which operate, that are running IoT systems. So you have an edge server managing resources, and then you have this edge server typically has an architecture, and often it's the point of entry, and sometimes a single point of entry for an IoT system. So that is where the attack is directed. So the attacks go towards the server, and so you see the structure we have there. Now, the software architecture of the server is below, and the server is up there. And of course, you have some kind of switch or a multitude of switches that connect the IoT devices themselves to the server, okay? And to the external points from which attacks can come. Now, what's quite interesting is that what we discovered, which is kind of a bit unusual, when people are very involved in data science aspects of attack detection, they look at the data sets and then they process them offline. They simulate their attacks offline and they do the learning offline. So everything is really done offline. We discovered by doing things online that the major effect of an attack is actually to disable the attack detector, slowing down substantially the attack detector. And we will see this in measurements that I will show you. So the attack detector, which is indispensable, okay, is being slowed down by the attack. And the way we found to, first of all, mitigate this first problem is by traffic shaping. So protecting the server through traffic shaping. So this is one of the ideas we have. There are several ideas in our work that we've kind of discovered over the years. One is that an attack detector should be trained on normal traffic. and not on all the different kinds of attacks, because there are just too many of them. You can't kind of specialize in everything. So we specialize on what's normal and then raise an alarm, which means that we're not able to identify what kind of attack it is. But at least we're going to say there's an anomaly. Okay, so this is one idea. The second idea is that the attacker actually disables, and most of the attacks disable the software on top of the platform, in particular, the attack detector itself, which is considerably slowed down because timely attack detection is essential. So because of that, we have come up with an original traffic shaping policy, okay, which is very simple to implement, so it doesn't introduce overhead. And it has the additional characteristic of preserving the end-to-end delay. That is, packets going into this traffic shaping policy are not, even though individually they're delayed, the delay from arrival until exit from attack detection is identical. It has neither been increased nor decreased. Okay? So traffic shaping is very important. And the third part is mitigation. What do you do when you've detected an attack, and what kind of measures can you take? And we're still in that process. Okay? And we work through, collaborations with industry. So we have quite a bit of use cases. So, we install whatever we do has been installed or is being installed in use cases. So the first step, what kind of mathematical model do you use for attack detection? You may be aware that one of the first neural network models in the world was invented by someone in France, in Paris actually, an MD, medical doctor, called Lapix. So there's a Lapix model, which is a spiking model. Now, this was a single neuron model, okay? And he was doing the analogy with electrical circuits, like RC circuits, very simple circuits. And that was the Lapix model. And it could show a spike coming out. And he was saying, well, this is a mathematical model, it's a differential equation model. This is a mathematical model for a single neuron. That was 1907. Then there was McCulloch-Pitts, 45, 46, 47. This model is, if you wish, a generalization of the Lapix model in the sense that it's a network, it's a stochastic network where you have, if you wish, Q lengths, which represent voltages. Okay, so if you have an excitatory signal, an excitatory spike that increases the voltage at the neuron that's receiving, and if you have an inhibitory spike, it's reducing the voltage at the neuron. And if the neuron has a positive, not zero, but positive, strictly positive voltage value, it can fire. It can send spikes to others. So it's a network model. And it has a very nice mathematical solution, a product form solution. So the basic model is an unbounded state space, a Markov chain. It's in continuous time, not in discrete time, because some neurons fire after 10 milliseconds, after others after 1.5 milliseconds, and so on. They all have different times. So it's a continuous time model. And it has a very nice solution, which is so-called the product form solution, which all of you who have done Jackson networks are familiar with. So you have a very nice product form solution, except, of course, that you need nonlinearities, and they are there. The nonlinearities are in the way you calculate the probability of firing. So QI is a probability that a neuron fires, and it's given by this system of nonlinear equations. QI equals a system because there are n neurons, so you have Q1, QA. Okay, so that's the model that we use for, this is a model that I invented that we use for learning. It has the nice properties of neural networks, which means that these models are universal approximators for continuous and bounded functions. And of course, the more neurons you put, the better approximation you get. Okay, the usual thing. All of this is published. And the particular model that we use for attack detections, at least in this work, is there. It's on the slide. So it's a system with it's a multi-layer feed-forward system, except that rather than have single neurons, at the nodes, we have clusters. So why we put clusters of neurons? We put clusters of neurons to increase the number of neurons. The more we have, the better the approximation. So we have this structure. Okay. In fact, the structure with each cluster is first of all calculated in terms of a finite number of neurons, and then this number is taken to infinity, which means that we have many neurons there, and it becomes a transfer function. So each of the clusters is itself a transfer function. And the algorithm, then we use this for learning, okay, and learning normal traffic. Learning normal traffic. Typically, we use traffic which comes from data sets, various data sets. That's typically what we do. But we also have a test bed where we generate artificial attacks, as well as artificial normal attacks. Okay? So we have that, all of that, and the algorithm used for, we don't use, although the random neural network is a nice gradient descent algorithm, including for feedback in the network, but we don't use that. We use actually a FISTA optimization algorithm, which is well documented. It was invented in the, I think, late 80s, early 90s. It's an optimization technique, and we use that for the learning, for the matching. And what do? We pass normal traffic, and we expect the output of the network to reproduce the metrics. Okay? And we use traffic metrics, as before in the previous talk. We're looking at traffic metrics here, and we use the traffic metrics to learn what is normal traffic. Okay? Now, just this is a bit more detailed. There's a decision process at the output, and it is statistically based. That is, you look at whether the output vector, okay, matched to the input vector, the difference between the input vector and the output vector remains between a set of whiskers of the that you predetermined. Okay, so you're looking at how much they remain within the same. I mean, what distance is whether you're preserving the distance or going outside the distance. And the results, for instance, one example, this is a botnet data set, and with about 107 distinct IP addresses. And here, this is kind of an evaluation of the algorithm, which is that I described, vaguely, AADRNN, auto-associated dense random neural network. Auto-associated because we're trying to learn the normal. Okay, so it's kind of an approximate identity mapping. And dense because we have densified the clusters of neurons by making them tend to infinity in each of the groups. Okay, and then you have the accuracy metrics on the data set. We get 99.84 accuracy. We get 0.02 false positives, etc., etc. And then this is compared to different techniques, including K-nearest neighbors, which is a very kind of robust method, but also very time-consuming. Okay, so this is the kind of thing we do, and let me just comment on what these 99 point whatever means. Okay? If you have 10,000 packets, you'd say, oh, this is wonderful, and so accurate, wonderful. But you have a significant number of packets that you've missed. Okay, so that's bad news. So let me say that there is still marginal improvement, right? So we're not there yet. We're not there yet. Even though everyone says this is wonderful, I mean, they go, point. No. The other thing is the false positives. The false positives are very bad news because you do everything in the false positive that you have to do if there's a real attack. And that's expensive. Okay? And I think our method is especially making things better, not wonderful, making things better at the false positive levels. Because if you look, for instance, at with respect to K-nearest neighbor, it's practically a 90% reduction in false positives. So this is a very positive side of this approach. But still, if you think that now we should stop working on attack detection, forget it. We still have to find better roads because these are just not accurate. So that's the general overview of the stuff. The other question, of course, is, okay, we've said, oh, we're wonderful people. Rather than study all different kinds of attacks, we will just learn what is normal and then work from there. Okay? Now, the question is, how good are we at detecting different kinds of attacks? Because you can have data sets where there are different kinds of attacks, and you want to find out how well you're doing. And the news is, it's always mixed. There's a good news and a bad news. The good news in this particular case is that for 37 different attack types, we did reasonably well. But in some others, we did deplorably badly. So there is probably something to be done in, for instance, if you have a method that is very good in general, which seems to be our case, good in general, but not good in particular everywhere, how can you mix a good research topic is how can you kind of combine methods so that you can cover your cover yourself for the things that you haven't been able to do properly. Okay, so all of that is kind of interesting. And here on the right-hand side, we're comparing with kind of a very good statistical method called support vector machines. So we're seeing that we're doing a bit better than that, but still, there are many, this is on all of the data, not just on the ones where we're good, on all of the data we compare. But you see that there are lots of attacks where we're not good. Okay? So how can you combine methods, fuse techniques, act adaptively as you move through data sets and so on? Of course, with the real data sets, none of them are stationary. So people who say, I'm going to have a nice attack generator, and I'm going to have a stationary process, which is so nice. This is really away from reality. Why? Take just a simple, stupid botnet. The simple, stupid botnet is fundamentally non-stationary. Why? Because it's increasing the number of participants in the attack, right? So how can it be stationary? So it's unstationary, and what we've been doing, for instance, other work that I'm not talking about today, we've been doing some other work where we look at how you can deduce the attack graph of a botnet. Can you take data sets and do the inverse problem of constructing the attack graph, okay, which is quite interesting. We've done some work. We show we can do it, but it's again with machine learning techniques, but that's a very interesting problem as well. Okay? So, and a much more detailed analysis must be carried out when you have, this kind of characteristic of a method is bound to happen. Whatever method you have, it's bound to miss some things. So how can you then delve deeper into certain aspects of your data sets so that you can identify attacks that you're not good at identifying by switching modes, by changing your method, and so on. So I think that's quite a bit of kind of a challenging and very interesting area to work on. I had mentioned that attacks are strange in the sense that they take down your, actually your operating system, slowing down your operating system, and then slowing down everything else that's running on top of it. Okay? And this is what we see. These are measurements. Again, with real attack data sets, what we have here is a fairly short attack on the left-hand side. I think it's a 10-second attack, which is ridiculously short. And on the right-hand side, you're seeing that the operating system is just swirling along. Okay? And what we're showing here on the right-hand side is the processing time of the attack detector. And you're seeing that, as time goes by, although most packets are kind of analyzed in a reasonable amount of time, as time goes by, you get worse and worse at being timely, at doing it fast. And you have these large delays. And these large delays are, in effect, mapped into the areas you see on the left-hand side where the queue is not being processed. The queue, there's a big queue of packets that have come with the attack. Okay? And the attack detector is trying to process these. But the attack detector is being slowed down. and therefore it stalls. Its work is stalled, and the queue only goes down when it does its work. Okay? So one of the challenges then, above it's kind of a longer time scale, below it's a shorter time scale, you do exactly the same thing. So the challenge is, what can you do to handle this? And this, I had mentioned that we do traffic shaping at the entrance of the attack detector. So, and these are more measurements. This is the histogram of the time needed to analyze a single packet, okay, at the attack detector when there is no attack. Everything is fine. This is the same histogram when there is an attack. So it has shifted to the right. And of course, you don't see the heavy tail here. You don't see it. It's way out. I mean, the big things that are jumping up, which are messing up the delays, you don't even see them. Okay? But you have shifted the average to the right, and you've also, of course, created a heavy tail. So you've changed the nature of the traffic, and that is slowing down your processing time. So the smart QDTP forwarder is the technique that we kind of invented to smooth traffic, and which seems to be working. And what we do is we implement it on a Raspberry Pi and sit it between the network and the server. Okay, so when everything is normal, it has nothing to do, it just passes things along. And when the attack happens, then it's protecting the server. That's its role, okay? It's the first line of defense. It doesn't eliminate the attack because we don't know, only the server will know, the attack detection mechanism will know when the attack is happening. On the other hand, this smart QDTP forwarder will preserve end-to-end delay, which is a very interesting mathematical property, but it will take care of things when the attack happens. All right, more about this. Now, the analysis of the smart QDTP forwarder is based on conventional queuing theory. Okay? So what you do is you construct Lindley's equation. Construct the Lindley's equation from the end-to-end, and then you construct Lindley's equation for the first part, which is the forwarder, and then you construct Lindley's equation for the attack detector. Okay? And of course, you know that the delay, total delay, is going to be the delay of the attack detector and the delay of the forwarder. Right? So this is the thing. And the what does the traffic shaping do? The traffic shaping is shown at the top of the slide. You can find this written fairly nicely in a paper we published at the International Communications Conference 22, nicely simply. Now, for some of you, they bring me back to some classes at OPSE where we talked about queuing theory. Forgotten already. When I was teaching at OPSE, we used to do these things, you know, in the queuing theory. But anyway, so the math is all worked out using conventional queuing theory, and this is work with my friend Carl Sigman, who is a professor at Columbia University in the industrial engineering department there. And the key theorem is basically that, you know, the introducing this thing does not change the end-to-end. So it has no cost, except of the hardware and of programming the algorithm. That has no cost, but has a benefit. And the benefit, you can see it here politely. The benefit is y-axis is queue length at the entrance of the attack detector. It's in the red if there's an attack. It's logarithmic scale. It's in the red if there's an attack, and if it's blue, it's in blue if there's no attack. And basically, sorry, it's in blue if there is, if it's in red if you don't put QDTP. It's in red if you put QDTP. So, red without, blue with, finding out traffic. So you have that, and you actually see the effect. So you are essentially protecting. The QDTP is absorbing the shock. That's where all the packets are sitting. Okay? and the attack detector is being protected and is operating at a normal rate. So the server does not have a shock, and the shock is absorbed by the QDTP box. Okay, that's that hardware box. So that's the idea. That's the engineering idea, and the theory follows. So that's nice. So you see what's happening for different attacks, and 10-second attack, 30-second attack, 60-second attack, etc., etc. So, and the QDTP has a parameter which is called D. Now, what does this parameter do? Very simple. A packet arrives, okay, and the algorithm looks at the time at which it released the previous packet and adds this constant D. If the arrival time is larger than that, then the packet goes forward. If the arrival time is shorter than the previous release time plus D, then the packet stays until the previous release time plus D, and then it is released. Okay, so it's facing things. What is really interesting is that the end-to-end delay is the same. It hasn't changed the end-to-end delay. So this is how it works. And the result then, you can see that the packet analyzing times have not changed too much. Before you had kind of this big shift to the right. Still now you have some shift to the right, but you have preserved, you have protected the system from the attack. Okay. So above you have with what you're seeing with and without, etc., etc. And you look at different values, and then that allows the attack detection system to process packets on a regular basis and shorten the release time, which has gone down from what it was before, which was a very long tail, thousands of seconds. And this is, of course, what you can do if you drop packets. So you can say, well, just simply brutally drop packets. But although you can do that, and many people will argue that's the best you can do, where do you drop them? They're all sitting in front of the SQF. And from there, you send an order, drop. Okay? Now that sounds reasonable, except that those packets may contain a lot of interesting things. One interesting thing, of course, is that they may contain good packets. Very often they're mixed. Okay? So what you'd rather like to do is to somehow be a bit more adaptive and waste less. And if you do that, of course, you have this big arrival of packets. On top of it, perhaps the attack has ended, new packets are arriving, and so on. So you may be kind of losing a lot of good stuff. And first and secondly, you don't know when the attack is stopping. You don't have that information. So what we propose, how much time do I have?
20 minutes.
Okay. So what we propose is an approach to mitigate the action of an attack. And the mitigation process is based on the following idea. When an attack happens, I will drop some packets. Okay, because the attack has happened. I know they will last some time. However, I will then sample again. See whether it has stopped or it is going on. If the answer is it's still going on, I will drop and then sample again a little bit. Okay, so I repeat this. And I give myself intervals of, say, M packets. Each M packets, I note the attack, I drop, and then I move forward later. I don't keep on sampling. I take a decision again and drop, and so on and so forth. So a progressive approach. And what is the purpose of the progressive approach? It has two purposes. One is to more finely understand when the attack, so that you don't keep on saying, well, this is an attack, I throw everything away, etc., etc. So you're being a bit more kind of careful about that. And the second is to minimize the two things: overhead on the one hand, because the more processing you do, the more overhead you're creating. And the second thing is to minimize the good packets that you lose. Okay? Because, you know, in your traffic, in your attack traffic, these will be mixed. The goods and the bads will be mixed inside this one. So if you do this thing, then you can at least, first of all, realize when it's not, this traffic is not attack traffic, and you can also realize when the attack is finishing, is ending. So we do that, and we try to do this in some optimum manner. So this is still quite rudimentary. Again, there's a lot of work to be done in, for instance, how many packets should I drop when I decide there's an attack, and which part should I try to save, which part should I drop, etc. All kinds of interesting questions. But here, what we're just looking at is the cost function, which involves the overhead of analyzing. Now, you must realize, I haven't mentioned it, that any attack detector doesn't examine packets packet by packet, but rather by windows of W packets. Okay? And recently, not importantly here, but recently we've been looking at very carefully at how large the windows. So we've been doing a lot better in statistics on number of packets that we should put in a window. But anyway, so here you have a window size of W, which is fixed. Okay, and what you're saying is, I'm going to look at a cost, which is going to be a mix of overhead and of packets lost, but which were good. Okay, so these two things together. So we put them into a cost function, and the parameter that we have to choose is the sampling rate. You know, how often, how many M packets, we take M packets bunches. After M packets, you sample again. After M. So the M is the parameter that you choose. And we're looking at how we should choose it, and then we look at the cost. So in this data, on the top we have the theoretical results, okay, which tell us, you know, how we should choose it. And at the bottom we have the same thing, the measurements on our test bed, and we're looking at, you know, how. And so we see roughly similar values between what the theory says and the experimental results say. So this gives you kind of a good view of what we do in that particular problem set. But we have been doing other things as well, and this stuff is published as well. And we're looking at, for instance, do we have fast techniques for looking at a network system, okay? And trying to decide, this has a hardware and kind of an architecture, and then a purely software corresponding aspect. And we've looked at both. Let me just kind of tell you something about, for instance, software vulnerability prediction. What they do, typically, is they do lexicographic analysis of programs. And one of the people who have done this is a French guy called Lionel, many years ago. He's now the director of L'Erol. L'Erol is the research center in Ireland, the computer science research center in Ireland. So what they do is they look at software and they do lexicographic analysis of the program, of the software, and determine whether the way it's being written generates vulnerabilities. Okay? So this is for individual software components. And what we did was to say, okay, so we know what the components are, but a lot of software systems are built out of existing components. People don't reprogram everything, right? So they take the components, they put them together in some way. This is calling, this procedure is calling that procedure. This one is exchanging parameters with that. That gives you a connectivity graph between the components. And what we try to deduce is whether, whether the system as a whole is vulnerable and to what extent, but also whether certain components' vulnerability is being modified by the vulnerability of others. Okay? To do that, we take a kind of we start with the data from the individual vulnerabilities. We also include information about how the components are connected, okay, because that's how the application has been developed. And then we associate with each node, which is nodes correspond to software components, and we associate with each node a yes/no, well, basically an adversarial network. Adversarial in the sense that one part of the network says yes, it's vulnerable, the other part says no, and they're in competition. So these are looking at each node, and based on the connectivity, all of these sub-neural networks are talking to each other. Okay? And we run this, and then we come up, it looks like a likelihood, in the sense that you're looking at the likelihood that one is stronger than the other, that the output of one is more affirmative than the other. Okay? And that allows us to determine, as a result of the whole connectivity, how each of the individuals are affected. Okay? And then we run this again through standard techniques for vulnerability detection and see whether the answer for the whole sticks with the individuals. Okay? This is work we published last year. I'm not a software engineer, but I've been working with colleagues in Greece who are, and so we've been doing this work with them. And this is basically the math behind it. So this is the other work that we do in this area, and then this has a kind of a direct network aspect, which is if we know, for instance, how vulnerable nodes are from their attack history, then we can try to infer how vulnerable the network as a whole is. And we've been doing this for the different IP addresses in the data sets we've been looking at. So that's interesting to look at, and we have various multi-component software work, and kind of interesting to see how we are able to kind of use methods from the network side back into the software system side. Oops, that's the end, I think, and I'll pause for questions, and I'm really happy to have a kind of a lively discussion.
Determining what is normal traffic is very difficult now, because in the web, for instance, there can be a lot of changes. So maybe this system is more adapted for a more controlled environment, like SCADA, things like that.
Well, our approach to saying this is normal traffic is not personal. It's not we who decide. You just take the data sets where we're told this part is normal and this part is not.
But in the web, it changes all the time.
True, but that's not how we train. We don't train with the web. We train with data sets which have been certified as having this part is normal, this part with attack, this part. And some data sets are labeled in this manner. So we don't kind of make up what is normal and what is not. We just take what the experts say, who have generated the data sets.
I have a few questions. First one is about the architecture. So you put the EDS between the switch and the server, and that give me the question about if the attack is targeting the server, like the botnet attack. I understand why you put it there, but if
why I put it where? I didn't understand what I'm putting.
The EDS, the intrusion detection system, the model.
The intrusion detection system. The intrusion detection system is put on a server, and it processes the incoming packet sequence into the processor. So you have a server We install it there, not because we have installed it, it's because a lot of people do that. I mean, I haven't invented anything about, installing intrusion detection systems on servers.
So it's just for attacks that are targeting the server.
Well, if you put it on a server, it detects attacks on the server. If you put it on a Raspberry Pi, it will detect server attacks on the Raspberry Pi. If you put it on a cloud system at the entity of the cloud system, it will detect attacks there. IDS, you can put it where you want to put it.
Between the switch and the server.
What I didn't understand what it means to clean that thing.
I think there's a traffic shaping system between the switch and the server, but the IDS itself is host-based, but on the network interface. So it's looking at packet incoming in the server.
We are the traffic shaper is different from attack detection. It doesn't do attack detection. It lets everyone go through, but at certain times. It changes the timing, but it doesn't do attack detection. Attack detection is still done at the level of a server with a specialized piece of software which has been trained to do that.
So you have a resource constraint. So
To avoid congestion.
Why do we do it? Is that your question? I don't understand what the question is.
why you put it on the server? No, I understand.
Why don't I put it on the server? Because it's too late. It's like saying I will put something where it's it's too late there. Put it before so that the server is protected. If you put it on the server, it's too late.
No, but it's
when you were talking about the mitigation system, you were talking about the build side of how much packet you consider and URL, etc. And you mentioned that the build side was space. And did you consider the case when you can change the build size and analyze the packets inside?
Yeah, we have done. We haven't published it, but working on that. Yes, we're looking at, and this is something that very often people don't publish and don't study. I mean, all of these attack vectors. Everything is highly parameterized. There are window sizes, there are details of the algorithm. So everyone assumes a window. Okay, and everyone takes decisions based on a few parameters. But that generally is not, if you look at the literature, that's not reported. I mean, why would they pick it like this? Oh, they say, I took it as 8 because 8 is a good number. I didn't want to take the 20, 20 is too much. Which makes sense. You kind of intuitively say that it's better to put like 10 than 20 or 100. Okay, 100 because you have kind of find out a lot of information. If you just have one, you have very little information. So you must find the optimal. And what we'll be looking at really carefully is, how the accuracy depends on this parameter. And it does.
Thank you for the clarification. I can see that this method will work for those attacks, for denial of service attack, but does it work for the other kinds of attacks where you don't have a lot of incoming packets?
Well, I'd like to tell you that you're right, but the data we have doesn't say that. I showed you data where many different types of attacks were being recognized. So I'm not fully, I mean, I would like to say you're right.
No,
I'm asking the evidence. I'm not a magician. I don't know the answers to all the questions, but I just deal with evidence. So the evidence is that it's not just for gospel. It works for gospel, but not just for that.
Thank you for your presentation. It's very interesting. I just want to ask that, of course, of any theoretical solution, our goal is at the end is to apply it in real life. So for such mitigation attack programs or for such environments, what do you think is better to use the datasets or traffic generation or to use the real-time traffic generator tools?
Well, I'll tell you what we did. And I think I said it. For the training and validation of the detectors, we use real data sets, okay, which have been produced by people who are supposed to be experts, and they have test beds where they collect the data and they publicize. Okay, and there are a lot of people who collect data but don't publicize. But there are a few that publicize. Okay, so that's what we use. So that's our approach. On the other hand, because we're running a lot of experiments, when we are in the lab, we can't just use one or two of them. We have to generate a lot of attacks. So we have attack generators, which we also use in our projects that we port to the use cases. So, for instance, when we did our stuff, when we took our algorithm to Technalia years ago, we didn't only, we took our software, we took the data sets, real data sets, but we also took our attack generator. So that's what we do. Personally, although, you know, in my life I've done a lot of simulation, I don't believe in simulation tools because of the timing issues. Because a lot of the simulation tools are packages, and the users, although they're open access, etc., they can look. It's very difficult. The person, I mean, you don't have time to do the spy on the software and see exactly what it's doing. You're not there to do that. It's just too much work. Okay? You really have to go into the whole details of the simulation packaging that you're using. So we do not use simulation. For pragmatic reasons, I mean, the simulation tools, it's very difficult to know whether their times are faithful, whether they're representative of something known. And if you wanted to find out, it's just too much of an effort. So,
thank you for the presentation. It was very interesting. I was wondering if we come back to the neural network that you presented. If I understood well, it was a spiky neural network, right?
it is one.
What? So the neural network that you presented at the very beginning,
Yes,
a spiky neural network. I'm correct?
You know,
No, not the network. It's a
nothing to do with it.
Okay, so you train it
It's
using.
the random neural network, and you can find it on Wikipedia. You can find it in the literature.
Okay, and so you train it using a standard back.
So the random neural network has a gradient descent approach that you can use, which is both, you know, which is n cubed if the network has feedback, which is n squared if it's a feed-forward network. But in this work, we did not use that. We used FISTA, which is an optimization technique for basically good for non-convex optimization. It creates, you know, it exploits local convexity. So that's what we use because it was faster.
Okay, thank you.
Yeah. Do you have any idea why your algorithm works well for certain kind of attacks and not for others?
Do we know why? We looked at data sets, okay, and we haven't done, because, you know, after all, we're a small team. We have a few students, so we can't do everything. So what we do is we kind of do this, and then we follow this up on this research and so on. So we don't kind of clean up everything and then move to the next step. So we don't know why, but certainly what we did, at least politely, take data sets that contain many different types of attacks, and we saw that we were good on many of them, but not good on a few of them. So, but we don't know exactly the reasons for it. And that, I think, would be a very interesting. And what I would do, provided I have time, is because I also have projects, so the projects require a certain number of deliverables and so on. So it's complicated. So what I would do is kind of look at within data sets what these attacks look like, and look at their differences with respect to the ones that we're good at detecting. And that might help us understand it. Look at the data itself, a bit like you were doing in your talk, when you were looking at, you know, what is happening in these data sets, which are so-called poisonous ones or which are different ones. So that, I think, is a good approach to understanding it, at least my impression. But I have learned. Perhaps we can collaborate.
When dropping packets is done in a random way, or
No, in a blocked way. So as you, because with the stream we have, you detect that an attack is occurring in the first few packets. Because the intrusion detection system is protected. So within 100 packets, it knows that less than that. It knows that an attack is happening. At that point, you drop whatever is there. But they continue coming.
so maybe it could be done using a policy, no? Like dropping packets that are less important.
It's hard to say which is less important. I mean, you can't spare bandwidth. The problem is in this system is that if you start doing things like you suggest, then the intrusion detection system will be even more strong. Because that takes computation, right? So you'd have to have spare processors or another machine or something else. That's the tricky part. But, you know, all these are good ideas, but, you know, how do you do them on one platform? Not almost. Because there is an attack, is the attack detector, let's say. Attack detector, wait a minute, now it's something else. And the attack detection stops. That's the tricky part. Scarce resources.
I have a question as well, because it's my workshop. No, but more seriously, so you have an approach with this QDTP traffic shaper, and I understand that it's packet-based, as you said, like you are going to drop n packets, for example. And so one of the objectives was actually reducing the overload on the intrusion detection system. In what we've seen this morning, a lot of the data sets themselves, and you have used them, are served on the flow-based formats. And have you compared your approach with a flow-based detector to see whether, I mean, what you've gained with the traffic shaper could be also gained through analyzing flows instead of packets?
Well, I mean, you could, but if you wanted to do it in a practical way, you could have a variable number of QDTPs. You should have a lot of them running together. Okay. And because we chose to put the QDTP on a cheap machine, I'm not going to have a server. I'm not going to buy myself a supercomputer to run QDTP. It has to be a much simpler device, which doesn't decrease the overall cost of the system. So if you have a simple device, having multiple instantiations of QDTP working for different flows may be just too tricky. Pragmatically, it may be difficult. Perhaps we can try when there are 2 or 3 and have a look. It's a good idea, but I think it's not generalizable with this kind of argument. In any case, the incoming flows will all here, in this case, they're all aiming to the same port on the server. Okay, so you must catch them before. Now you have to have a Raspberry Pi that is identifying flows and then putting them in different instances of the algorithm. And that's an idea, and perhaps a good PhD topic.
Thank you. Yes, sir.